Hello everyone. Today we are going to discuss about the short answer questions with answers for the mid-2 examination. Okay, in the mid-2 examination, we are going to discuss the last 2.5 unit short answer questions with answer. Now let's discuss. The first question is, draw the VA characteristics of PN junction diode. So these are the VA characteristics of PN junction diode, which is having the forward bias characteristics as well as the reverse bias characteristics. It is a forward voltage on x-axis, and it is a in the reverse side reverse voltage. It is a forward current and it is a reverse current. Reverse current we have to take in microamps. In the forward bias, up to this point there is no conduction. After this point it starts conducting. In the reverse bias, up to this point there is a small leakage current flows. Okay, if we apply the voltage beyond the breakdown voltage, the current increases drastically. These are the reverse bias characteristics, and it is a cut-in voltage. This point is called as a cut-in voltage, and it is a knee point. Okay, this is about the VA characteristics of PN junction diode. In this particular question, just you have to draw the diagram and you have to indicate the parameters. Next, draw the VA characteristics of germanium and silicon. Now, in this question, we have to combine both the germanium and silicon diodes VA characteristics. If we combine both the characteristics here, we will get the VA characteristics like this. It is a forward voltage and it is a reverse voltage. It is a forward current and it is a reverse current. If we take the silicon diode, we know that already the cut-in voltage of silicon is 0.7 volts. The cut-in voltage of silicon is 0.7 volts, so it starts conduct from the 0.7 volts. While in case of the germanium, the cut-in voltage of germanium is 0.3 volts. It starts conduct from 0.3 volts. Okay, and it is the reverse bias characteristics of the silicon, and it is the reverse bias characteristics of germanium. This is about the germanium. If we combine the germanium and silicon characteristics, we will get the characteristics like this. Next one is, what is cut-in voltage of the diode? Okay, the forward voltage at which the current through the junction start increasing is called the cut-in voltage. Cut-in voltage for the silicon is 0.7 volts, while germanium is 0.3 volts. The cut-in voltage is denoted by V gamma. So the voltage where the diode starts conducting is called as a cut-in voltage. It is 0.7 for silicon, 0.3 for germanium. What is reverse breakdown voltage of the diode? It is the reverse voltage at which the breakdown of the junction takes place and the reverse current increases rapidly is called as reverse breakdown voltage. Here, this reverse breakdown voltage is denoted by VBR. VBR, reverse breakdown voltage. Next, what is knee point? The forward voltage at which the current through the junction start increasing rapidly is called as knee voltage. So this particular knee voltage is nothing but at this point the voltage increases rapidly in the forward bias. That is called as a knee point. Next, what is depletion region? So in between the forward bias, in between the P-type layer and the N-type layer, there is a junction. So that what is that junction? He is asking what is depletion region. Depletion region or depletion layer is a region in a PN junction diode where no mobile charge carriers are present. Depletion layer acts like a barrier that opposes the flow of electrons from N side to N side and holes from the P side. Okay, it acts like a barrier in the junction. That's why it is called as a depletion region. What is reverse leakage current? The reverse leakage current in a semiconductor device is the current from the semiconductor device when the device is reverse biased. When it is reverse biased, we will get the reverse leakage current. Next, draw the ideal and practical equivalent symbols of the PN junction diode. If we take the ideal diode, this is the ideal diode. When it is in forward bias condition, that is positive terminal given to the P type and the negative terminal is given to the N type, then the equivalent circuit will be drawn like this for the ideal diode. If it is reverse bias, that is when the negative terminal is given to P type and the positive terminal is given to N type. If we reverse the terminals, then the diode will be in the reverse bias condition. When the reverse bias, the equivalent circuit is like this: open switch. It is a closed switch and it is an open switch. Now, if we take the practical diode, in practical diode, if the diode is in forward bias, that is positive terminal is given to P type and the negative terminal is given to N type. Then the diode is in forward bias. In forward bias, it is replaced with cut-in voltage that is connected in series with RF, B gamma. This is forward bias condition. Next, if we take the reverse bias, in the reverse bias, the terminals will be reversed. It is a negative terminal and it is a positive terminal. Negative terminal is connected to P, positive is connected to N. Then the diode is said to be in the reverse bias. In the reverse bias, same like ideal diode only, to replace with open switch. These are the equivalent symbols for the PN junction diode, ideal and practical diodes. Next, what is diode current equation? The diode current equation expresses the relation between the current flowing through the diode as a function of voltage applied across it. Mathematically, the diode current equation can be expressed as I is equal to I naught into e power qv divided by eta into kt minus 1. This is the diode current equation formula. Just is asking write the diode current equation. In this, I is nothing but the current flowing through the diode. Here I naught is nothing but is the saturation current, that is reverse saturation current. And Q is a charge on the electron. This Q is called as a charge on the electron. And V is the voltage applied across the diode, this V. Next one is eta is called as a exponential or ideality factor, and it is 1 for germanium and 2 for silicon. K is called as a Boltzmann's constant, and here T is called as absolute temperature with respect to Kelvin. This is about the diode current equation. Now next one is define drift and diffusion current. First we will discuss what is drift current. When the charge carriers are moved in a semiconductor due to the applied electric field, the resulting current is known as drift current. It is a current flows in the semiconductor due to the applied electric field. Then it is called as a drift current. Then when in case of diffusion current, the electric current in a semiconductor caused by the flow of charge due to the concentration gradient of the charge is known as diffusion current. This is due to the applied electric field and it is due to the concentration gradient of the charge is known as a diffusion current. Next, what is rectifier and the classification of rectifiers? Rectifier is an electronic circuit which can convert AC into the pulsating DC. The pulsating DC is nothing but DC plus AC ripples. Or the rectifier we can also define as rectifier is an electronic circuit which can convert bidirectional wave to the unidirectional waveform. So if you see the classification of rectifier, there are two types of rectifiers, half wave rectifier and the full wave rectifier. Again, in full wave rectifier, there are two types. That is center tapped center tapped full wave rectifier and the bridge full wave rectifier. These are the classification of rectifiers. Next, define ripple factor. The ripple factor is defined as the ratio of RMS value of the AC component to the DC component. The ripple factor functionality is to explain how much amount of AC ripples present along with the DC output. Generally, at the DC, we are having not pure DC, that is called as a pulsating DC. That pulsating DC is nothing but DC plus AC ripples. By using this ripple factor, we can find the how much amount of AC ripples are present in the output DC. This ripple factor is denoted by gamma. The formula is VAC to the VDC. And VRMS square divided by V average square minus 1. And for the half wave rectifier, ripple factor is 1.21. And in case of the bridge full wave rectifier and the center tapped full wave rectifier, in both the full wave rectifiers, we will get the ripple factor is 0.48. The ripple factor is improved in the full wave rectifier. Next, what is peak inverse voltage? The maximum value of the reverse voltage at which the rectifier has to withstand during the non-conduction period. In the reverse bias condition, we will get the peak inverse voltage. The peak inverse voltage of the half wave rectifier is Vm, and peak inverse voltage of the center tapped full wave rectifier is 2Vm. Next, in case of the bridge rectifier, is the peak inverse voltage will be improved, that is Vm. So this is about the peak inverse voltage. Next, draw the circuit diagram of half wave rectifier. This is the circuit diagram of half wave rectifier. This is a supply voltage. Okay. It is a diode D, and it is a RL. Across this load resistance, we will measure the output voltage V0. And it is a transformer primary winding and it is a transformer secondary winding. This is about the circuit diagram of the half wave rectifier. Just is asking draw the diagram and draw the circuit diagram of the center tapped full wave rectifier. This is a circuit diagram of the center tapped full wave rectifier. It is a supply voltage Vs. Supply voltage Vs, that is AC. Here also it is AC supply. It is a diode D1. It is a diode D2. It is a minus plus V0 output voltage we will measure across this load resistance. RL is a load resistance. It is a transformer primary winding, transformer secondary winding. Here we are taking the tapping at the center of the transformer. That's why it is called as a center tapped full wave rectifier. Next, draw the circuit diagram of bridge rectifier. This is a bridge rectifier circuit and it is a supply voltage, AC supply, and it is a transformer primary winding, secondary winding. This is a step down transformer. As the DC voltage levels are very low, that's why we have to use a step down transformer only. Secondary winding should be less compared to primary winding. Here it is D1, D2, and D3 and D4. There are 4 diodes. Okay, in the bridge rectifier we use 4 diodes. In the center tapped full wave rectifier 2 diodes, half wave rectifier 1 diode. It is a minus terminal and it is a plus terminal and it is V0 and it is RL. RL, that is load resistance. Voltage we will measure, output voltage we will measure across this load resistance. This is the circuit diagram of the bridge full wave rectifier. Next, to define efficiency and what is the efficiency of all the rectifiers. The rectifier efficiency is the ratio of the output power to the input power. Here, efficiency is denoted by eta, that is the power output divided by power input. power output divided by power input into 100. For half-wave rectifier, the efficiency is around 40% we will get. If it is for center tapped full wave rectifier, for center tapped full wave rectifier, we will get 81%. At the same time, for the bridge full wave rectifier also, we will get the efficiency is 81% only. It is a center tapped full wave rectifier and it is a bridge full wave rectifier. 81% we will get. Next, draw the VA characteristics of Zener diode. So these are the VA characteristics of Zener diode. It is a forward voltage and the forward current. These are the forward bias characteristics. Up to this voltage, there is no conduction. After cut-in voltage, it starts conducting. These are the forward bias characteristics. In the reverse bias characteristics, up to this voltage, there is a small leakage current flows. After this, if the voltage increases beyond this breakdown voltage, current increases drastically. This region is called as a Zener breakdown region, and it is the reverse bias characteristics, and it is the reverse voltage, and it is the reverse current. Next, draw the VA characteristics of SCR. So these are the SCR characteristics, and it is a forward voltage, and it is a forward current, and it is a reverse voltage and the reverse current. Here the characteristics are up to this voltage. This is in the forward blocking mode. If we apply the gate signal, it starts conducting. Okay, when you increase the Ig to Ig1, it will start conduct from this position. If you increase Ig1 to Ig2, it starts conduct from this position. And when we give the gate signal, it will go to the forward conduction mode. Next, in the reverse bias, up to here, there is a small leakage current flows. After this, if you increase the voltage beyond the breakdown voltage, the current, reverse current increases rapidly. This region is called as a reverse blocking mode, and it is a reverse leakage current. This is the VA characteristics of SCR. Next, why the Zener diode acts as a voltage regulator? Zener diode can generate the constant output voltage in the reverse bias with the variation in the input voltage and the load resistance. Hence, the Zener diode acts as a voltage regulator. Even if you increase the load resistance and the input voltage, the output voltage is constant. There is no change in the output voltage. Hence, Zener diode acts as a voltage regulator. So in the reverse bias, we will get the characteristics like this. Up to this voltage, if you increase the input voltage or the load resistance continuously, the output voltage is constant. As we are getting the output voltage is constant, then the Zener diode acts as a voltage regulator. Define transformer utilization factor, and what is the transformer utilization factor of all the rectifiers? The transformer utilization factor TUF of a rectifier circuit is defined as it is a ratio of DC power available at the load resistance to the AC rating of the secondary coil of the transformer. Next, here for half-wave rectifier, the transformer utilization factor is 40% we will get, and for the center tapped full wave rectifier, this transformer utilization factor we will get around 81%. While in case of the bridge full wave rectifier, we will get here same as center tapped full wave rectifier only. So it is a DC power output to the transformer secondary winding power. Okay, this is about the TUF, that is transformer utilization factor. Next, what is transistor and the classification of transistor? Transistor is an semiconductor device which can transfer the signal from one resistance region to the other resistance region. That is, transfer a weak signal from low resistance circuit to the high resistance circuit is called as a transistor. Okay, there are two types of transistor. One is unipolar transistor and the second one is a bipolar transistor. Next, what is bipolar transistor? Bipolar transistor means the bipolar transistor is a semiconductor device in which the electric current flows due to the both electrons as well as holes. Okay, the examples of the bipolar transistor is BJT, bipolar junction transistor. BJT means. Again, the BJT is classified into two types, NPN transistor and the PNP transistor. Next, what is unipolar transistor? The unipolar transistor is a type of transistor in which the electric current flows due to the only one type of charge carriers, that is either electrons or holes. The examples of UJT is unijunction transistor and the FET, that is field effect transistor. These are the examples of unipolar transistor. Next, draw the symbols of PNP and NPN transistors. So this is the NPN transistor and it is a symbol, okay, which is having the three terminals, that is emitter, base and the collector terminal. Here also it is a base terminal and it is the collector terminal and it is the emitter terminal. As the here it is the emitter current direction is outside in the NPN transistor and the remaining currents are inside. Base current and the collector currents are inside. Next, in PNP transistor also having the three terminals, emitter, base and the collector. In PNP transistor, emitter current direction is inside. As the emitter current direction is inside, remaining currents are outside in the PNP transistor. Next, why the BJT is called as a current control device? In the BJT, the output current equation in terms of the gain and the input current and IC naught, reverse saturation current, is given by output current is equal to gain into input current plus 1 plus gain into IC naught. Here IC naught is called as a reverse saturation current. If we write the formula here, in case of common emitter configuration, the output current of the common emitter is IC and the gain is indicated by beta and the input current is IB plus 1 plus beta into IC naught. This is the output current equation of the BJT. Here output current IC is depends on the input current. That's why it is called as a BJT is a current control device. Output current IC depends on the input current IB. Hence, BJT is a current control device. Next, relation between alpha beta in the transistor. Okay, alpha is equal to beta by 1 plus beta and beta is equal to alpha by 1 minus alpha. This is the relation just we have to write. Next, what is amplifier? Amplifier is an electronic device that is used to increase the power level of the input signal. It is known as an amplifier. A transistor acts as amplifier in the active region. In active region, emitter junction is forward bias and the collector junction is reverse bias. In this region, transistor acts as amplifier. Simply increasing the signal strength is called as an amplifier. Next, to define stability factor. Stability factor is defined as the ratio of rate of change of collector current with respect to IC naught at constant VBE and beta. It is denoted by the letter S. Here, S is equal to dou IC by dou IC naught at constant VBE and beta is equal to constant. Okay, here when S is equal to 1, that is called as a stable operating point, that is a stable transistor will be in the stable condition. When stability factor is not equal to 1, then the transistor will be in the unstable condition. This is about the stability factor. Next, define active region, saturation region and the cutoff region. First, saturation region. In saturation region, it is the emitter terminal and the base terminal and the collector terminal. It is having the two junctions, emitter junction and the collector junction. In the emitter junction is forward bias and the collector junction is also forward bias. Because of the both the forward bias, more amount of forward current flowing in the transistor. In this region, resistance is very low and the transistor acts as on switch. Because of the both the regions are forward bias, transistor acts as on switch. This is called as a saturation region. In cutoff region, this is the emitter terminal and it is a base terminal and a collector terminal. It is the emitter junction and here it is collector junction. In the cutoff region, emitter junction is for reverse bias and the collector junction is also in the reverse bias condition. Due to the reverse bias of the both the junctions, the current flowing is very low. The resistance offered in this junction is very high. That's why the in cutoff region transistor acts as off switch. Active region. In active region also, it is emitter, base and the collector. This is the emitter junction and it is a collector junction. In active region, emitter junction is forward bias and the collector junction will be in the reverse bias condition. One is forward and one is reverse bias condition. Due to the forward bias of the emitter junction, the current flows in the emitter junction is very high, and due to the reverse bias of the collector junction, the current flows in the collector junction is very low. As it is forward bias, emitter current flows in the emitter junction is very high. As it is reverse bias, current flows is very low. In active region, transistor acts as amplifier. Amplifier means increasing the signal strength is called as amplifier. Okay, this is about the all the regions. The next question is draw the input and output characteristics of CE configuration. In common emitter configuration, the input characteristics are drawn between input current and the input voltage at constant output voltage. Here, input current is IB and the input voltage is VBE, and the output current is VCE. If the output current increases, the characteristic shift towards right side. Next, output characteristics. These are the output characteristics. Output characteristics are drawn between output current and the output voltage at constant input current. Here we will get the characteristic like this. These output characteristics are having three regions: active region, saturation region, and the cutoff region. Next, draw the output and input characteristics of common base configuration. In the common base configuration also same, the characteristics are drawn between input current and the input voltage at constant output voltage. Here, if you increase the output voltage from VCB1 to VCB2, the characteristics shift towards left side here. That is only the difference from the remaining configurations. And next, if you see the output characteristics, the characteristics start from the negative region. Okay, here it is also having the three regions: active region, saturation region, and the cutoff region. The output characteristics are drawn between output current and the output voltage at constant input current. Next, draw the input and output characteristics of common collector configuration. In common collector configuration also, the characteristics are drawn between input current and the input voltage at constant output voltage. If you increase the output voltage, the characteristics are shift towards the right side. Next, these are the output characteristics of the common collector configuration. These characteristics are drawn between output current and the output voltage at constant input current. And it is also having three regions: active region, saturation region, and the cutoff region. And these are about the short answer questions with answers for the mid-2 examinations. If you able to read all the questions, then you can attempt all the short answer questions in the mid-2 examinations.